بسم الله الرحمن الرحيم. السلام عليكم على طلاب. If you can listen, if you listen me, if you can have my voice, just put something, acknowledge in the box if you have my voice. Okay, I hope you are all fine and sorry for the delay. Without further ado, we start our class today because we also started a little bit late, so we are just a little bit in a limitation of time. Here until now in the previous class we talked about the encryption, okay, رمزنگاری, encryption, and so far we came to one-time path, but for you to remember what we already discussed, I start a little bit earlier from the beginning of the methods of encryption. If you remember, we had I will write in the notepad, we had substitution, okay, we had 19 and 20. Okay, I will check to see what is 19 and 20. Substitution, we had transposition, we had XOR, okay, and then we had product. These were the different encryption methods that we were trying to explain each of them and bring some examples about each of them. So a slide 90 to 20, it's a bit, oh, okay, 19 to 20. Okay, I will start from there. I will go back a little bit from here, 19. So we can start from 15. Okay, scissor cipher, which I can go a little bit further. Classical substitution. This is the beginning of the substitution. Okay, so here we have again, I will explain for you. We have you can take a look at the note 5. We have substitution for the methods, we have transposition, we have XOR, and we have products. There are 4 things that we are going to discuss. Okay, so we can put that this is A, and this is B, and this is C, and this is D. The product is D. Okay, the first thing that we are going to discuss as a review from the previous session, it's we start from A. A is substitution. Substitution means that you take something and you put something else instead. For example, if you have A, B, C, D, okay, 1, 2, 3, 4, you remove A and put it 1 instead. You take B and put 2 instead. You take 3, put C instead, and so on and so forth. So this is the kind of encryption that we call them substitution encryption. As an example for substitution encryption, we talked about the Cipher method. In Cipher method, we use one number as n. We use one number as n to replace one letter with the letter that its location in the here in the alphabetic order is n number after or n number before the specific letter. For example, you see this is A, B, C up to Z we have here, okay, and then when, for example, the n is 0, okay, when the n is 0, you take A and instead you put A, okay. When the n is 1, you should take A and instead put B, something like that. So when n equal to 1, I just use this method to encrypt my name, and you can also do that that I make sure that everybody understood the meaning. So R, after R is U, okay, and after E is F, and after Z is A, and after A is B. So this is my name. Okay, you try your own name with n equal to 1. So the method is a Caesar cipher and the n is 1. So Rasha becomes R S, A B yes, S T yes, H I and A B. Yeah, okay, perfect. Ali, A B, L, after L is M. Ali, your name, just double check. H, I, no, Haydar, it's not correct. After H is I. And then after A, no, Haydar, it's totally wrong. N is equal to 1. Ali, also you made a mistake. Do it again. Others, BMJ, yeah. For Ali, AB, LM, yes, IJ. M is Muhammad, M is N, not P. Okay, let me explain for you again. Here in this example, okay, in this example, N is 3. But in my example, N is 1. So that's wrong. Muhammad, yours is wrong. In my example, just use N as 1, not M. Okay, N as 1. Anyhow, so you, Hussein, H-I, yes, U-V, yes, S-S, S-T, yes, E-F, yes, Hussein, thank you. Yours is correct. Okay, N is 1. No, Muhammad, N is 1. In my example, N is 1. You should replace 1 with the next one. Okay, so the next thing is that because when you shift, you have 25 different combinations. So you can have N from 0, which is the same thing. Okay, you can have N1, which shifts, this was our example. You shift letters by 1, and you can have N as the maximum is like N equal to 25. Okay, from 0 to 25, 26 different combination. Okay, 26 different combination. This is one method. But the other method is to use math. Math in Arabic is riyaziyat, okay, as in Persian. You can use khawas riyaziyat, okay. You can use the features of math or feature of mathematics that you can make the system more complicated. Okay, with this one, with using the math, you can make the system more complicated. The first method is that we use mode, or we say peymane. Okay, in Farsi we say peymane. Okay, or in English we say module, and it's about using the remainder. Okay, remainder in Arabic, I think it was baqiya. Okay, yes, okay, remainder. So if you use remainder, if you use remainder, those that they have same remainder, they can be same. For example, I will go to the board. First, I try to explain it in the base 10, okay, and then I will explain it in base 26. Okay, so in base 10, you see when you have 10, okay, and you divide it by 10, the remainder is 0. Okay, if you have 10 and you divide it by 10, the remainder is 0. So what about 100? What is the remainder? Not multiplication. Yes, it's 0. It's 0. Remainder. We only need بقیه. 0. Okay. What about this number? What is the remainder? 0. Okay. So in base 10, we can say, I will write it in the note. We can say 1 is equal to, no, 0. 0 is equal to 10, is equal to 100, is equal to 1000, and is equal to any number that they have remainder of 0. Now, we have infinite numbers that all of them, the remainder is 0 and they are all same. Okay, they are all same or similar. What about, I use another example. What about 12? Okay, what is the remainder? 2. Okay, and 1002, again remainder is 2. And then this number, again 2. What about this number? Again 2. You see, all of them, the remainder is same. So we can say in modulation of 10, so the 12 is equal to 22 is equal to, I don't know, 1002 and equal to 111 and 2, and this number, something like that. Okay, you got it? Okay, now you see in base 10, if I give A 0, okay, and I give B 1, yes, 2 also can be. Yes, Rasha, 2 also can be. It's okay. Okay, and C is the one with the remainders of, I don't know, for example 3. Okay, consider that we have this one. Okay, so instead of writing A, because if you write, you encrypt A to 30, you can encrypt A to, for example, 000, 010 and 1000, something like that. Okay, so you can use any number, any big number or small number instead of A, that they have there, for all numbers that they have same remainder or the بقیه is same. Okay, you got it? Now we go to the base 26, because why we use base 26? Because A to Z can be 0 to 25. Okay, A to Z. So we use the remainder of, for example, 26, بقیه, or remainder of 26. So for the remainder of 26, No, it's not the scissor itself. It's the upgraded scissor that make it more complicated, Ali. Okay, it's just we change it to make it more complicated. Scissor already finished. Okay, these are different other ways. Okay, so in base 26 we say that, for example, we can use 0 divided by 26, so the remainder is 0. But if we have, for example, 26 divided by 26, the remainder is again 0. And then when you have 52, if I'm not mistaken, divided by 26, again the remainder is 0. Okay, and you can go on until any number that you want. Okay, it's infinite. So again, in this system, instead of using, for example, encrypting AAA to 000, you can encrypt AAA to any random number that you want, but the remainder should be 0. For example, instead of the first A, I use 52. Instead of the second one, I use 26. And instead of the third one, I use calculator. For example, 5 multiply 26, it's 130. So this is the 3A. Again, if I ask for ABC, okay, if I ask for encrypting ABC, instead of A, you can use, for example, 5 multiplied by 26, it's 130. You can use for B 131, or you can use 027. Okay, and for C you can use, C is 002. Okay, this is random. Any random with the same remainder can be used. Okay, any random with the same remainder or barrier can be used. Yes, the base is 26. So the people said that it's not clear. You see what happens when you have 130 and you divide it by 26. Oh, sorry, 130 and you divide it by 26. What is the remainder? What is R? Okay, 0. Okay, and the next one, after 136 I wrote 027 divided by 26. What is the remainder? Is 1. Okay, and the third one, 002 divided by 26. What is the remainder? Okay, 2. So this one is A, this one is B, and this one is C. Okay, everybody okay? Okay, alhamdulillah. And the next thing, another method that we can use, I should go back to the slide. You see, another method that we can use is that, so we can use the shifting of the letters. We practiced that one. I gave you some examples, and we can use the numbers, and instead of the numbers we can use mode of the numbers or modulation of the numbers. This is another method. And also we can use negative numbers and positive numbers. It's easy. For example, if you use n is equal to -1, okay, what happens to c with n equal to -1? C becomes B, okay? And then what happens to Ali? Just encrypt it. Yes, thank you. It's ZKH. No, with n -1. Ali becomes ZKH, okay, -1. So you can use negative numbers, you can use positive numbers, you can use any numbers that you want to use or you wish to use. But we said that that's the problem, okay? We said that that's the problem because of the characteristic of the languages. And also another one, I forgot about this one. Another one is that instead of using numbers, we use the whole characters as cipher, you see. So the key is this one, okay? We use the whole characters and the key is this one. So when we say that the A is D, okay, it's not, there is no guarantee that the L, for example, is again the next one. L can be S, okay? No, in any language you can use, but the number or modulation changes. How many characters do you have in Arabic? How many letters do you have in Arabic? 28, okay? So you should use mode 28. Okay, and you should write the letters separately. For example, when you want to write Ali, okay, and you want to do the encryption, it's that you should write it like this. Then you can use. It's better that you write it separately, okay? And for example, in Arabic with the N1, what happens to Ali? N1. I think after Ain is Re, right? And after Le is M, and then after Ye, I don't know, it's Aleph again, right? It's A. Yes, Hossein, there is a difference. Yes, there is a difference, but it depends on the sender and the receiver. How they, what do they agree on? They can agree that they take the same thing, or they can agree that they take it as a different letters. Okay, it depends on them. Okay, it's like a contract. Okay, that we call that contract. It's on the contract. We call that contract protocol. Okay, we call it security protocol. Okay, let's go just to the next thing. So the cipher is the whole letters. You just mix the letters. Okay, mixing means in Arabic, mixing means khalt, I think. Yeah, khalt. Okay, you can mix all the letters, no relation, so no number, okay, so no number, and then because there is no number, it's, you should have the whole letters to have the key. Okay, so using this one, using this method, okay, just convert your own name only with this method. Let me Okay, I didn't say anyone does it, so I will do my own. You see, my name is Reza. Okay, instead of R, I should use Y. So it's Y, and E is F, and Z is N, and A is D. This is my name using this method. Oh, it's again Reza, and then I will write it again. I deleted R Y E F Z N and A D, something like that. Okay, you do your own name. Russia is R, it's Y, yes. A is D, yes, thank you Russia. Ehsan, W, E is F, I is W, yes, H is J. Okay, thank you. Yes, Ali is always easy. Ali, A D, and then L is S. Yes, Ali is easy. Thank you very much. Saleh. Okay, S is A. Saleh is A. Yeah, it's correct. Okay, so this is another way that instead of the combination, because there in the previous section, the computationally you had 25 different combination. Okay, in the previous methods you only had 25 different combination. Okay, in using this method you have 25 factorial combination, so it's bigger than the previous one, so it's good. So this is it. You see, or 25 or 26 is not important. 25, 26 factorial, which is a big number compared to the previous one. But we said that in languages we have patterns, okay, or in Farsi we say olgu. In languages we have, it's not important. Yes, Ali, it's not important. One is, you can include 0 or you cannot include 0, because factorial of 0 is 1. So it can be 26 or 25. The important is factorial, not the number. Okay, so everything has pattern. The next thing that we will discuss, everything has pattern or namat. So when we have, yes, namat, when we have namat, okay, in language, in for example, if it's audio, it has its own namat. Okay, if we have video, it has its own namat. If we have MP3, its own namat. HTTP, its own namat. And also human language like Farsi, Arabic, French, Germany, they all have their own namat. For example, in English it's like that. Number of the repetition of the different letters are different. For example, E has the most, it appears the most frequent, or has the most frequency in appearance, okay, in the English texts. And after that is A, and after that is, for example, T, and so on and so forth. And that's why using these patterns you can easily break the code without knowing the algorithm. Okay, you can realize or understand the code without knowing the algorithm. So for example, this is just an example. If you have a encrypted text like this and you just count the numbers, it's add something like that, okay? You just count the number of appearance, okay? For example, you count how many letters you have, and the most frequent letter is for E, okay? You can find the most frequent letter is E, and after that it can be T and A, so you can get TH and you can get THE, okay? And you can get A, and then you can get this and you can get that, okay? Because you have TH, and then everything will be clear very easily. It says that because of the number that appears, it depends on the numbers, okay? Because in the slides they already counted the number. For example, which letter has the most frequent number, okay? So they guess that P and Z are E and T because they are more frequent, and then ZW and ZWE, they are TH and THE, and then that you can break the encryption easily. You can break the encryption easily. So it's like that. Okay, and then Zulfaqar, I didn't understand what does n equal to 9 or 11 means, because it's encrypted and we don't know the n. Rasha, we count, okay? We count the numbers. You cannot do it right now, okay? You cannot do it right now. You need computer. Okay, you cannot do it right now. For this example, you cannot do it on your own. You need computer to count the number of appearance of each letter. Then you compare that the biggest one is it should be E, and then after that it's A, and after that it's C, something like that. Okay, the next one, it's there are methods that they use XOR, okay? The next methods are the methods that they use XOR, and example for these methods is one-time pad. So in this method, something that we do, the first thing you should do is that, let me go back to the board, okay? For example, you have characters. I use Ali because it's easy. You have characters. You should change the characters to bits. For example, characters can be, each character can be 1 byte or can be 2 bytes. Okay, it's each character can be 1 byte or 2 bytes. Okay, when you convert it to binary. So when you convert it to binary, it can be 01010111. For example, it's just Ali, just A. Okay, I take just A. This is A. Okay, and I can also be 0101 and something like that, for example. And then you use XOR, and then you need a key. You need a key equal to the number of bits. Consider that, for example, if it's 8 bits, yet the key can be 8 bits. If it's each character, it's for example 16 bits or 2 bytes, you should use a key like 2 bytes. And then you XOR this one with the, for example, this is the key and this is the key. You XOR these two with the key. Exactly. 0 and 0 0, 0 and 1 1. Exactly. Yes, it's correct. Thank you, Saleh. Thank you, Hossein. Okay, so you get the result, and result will be binary. For example, they should be like this. Okay, something like that. The result is binary, and you say that you already encrypted the characters. When you want to, so this is the encrypted text. Encrypted text. When you want to decrypt the text, you get the key 1010101010. Okay, and again 1010101010. You get the key. You divide the bytes, and then again you get the result. XOR it with the key, and again you get XOR. Okay, and something that comes here is, for example, this one. Okay, and this one is A. So this is the method. We call it one-time path. It means that each time or at one time you apply XOR on the bits of the text and you get a result. Okay? Okay. So again, I will go quickly through it. You get the character from here. Okay, you convert it to binary. Hossein, for all words you use the same thing. You use same key. For example, if your key is this one, okay, if your key is this one, you use the same key for all words. There is a table for characters. It's a standard in all of the operating systems, and we call it Unicode. Okay, we call it Unicode, or we call it, and we have ASCII, two different systems. Okay, for Unicode it's 2 bytes for each characters. For ASCII it's 1 byte. It's a standard. Sorry, 1 byte. It's a standard. Okay. If by binary, yes, you should only use binary, because if you use other numbers you cannot use the XOR operator. XOR only works on binary. So you should, the first you have the character, second you convert it to binary, third you should have one key, apply the key on the each characters. For example, the first, the second, the third, you get the encrypted text. For decryption, you separate the bytes, you apply the key, and you get the original characters. Okay, so let's go back to the next slide. This is one-time path. It's like this. You get the characters and you apply. You see, this is in this example I use the same pattern for A. For example, for one letter, okay, I use the same pattern, but I use different keys for XOR, and you see that the result is totally different. So it depends on the key. How, yes, the character is same, but the key are different. I just wanted to show you that depend on the key, the result will be different. and it's important for us in the encryption. The result is totally different from the original one. Okay, it's unbreakable because the ciphertext bear no statistical relationship to the plain text. We already discussed its random key of the same length of the text or the character can be used. It's easy to use. And the only problem is that you must make sure that you produce or you produce in Arabic, produce yantaj, okay, yantaj and distribute the key. Yantaj and distribute. What is distribute in Arabic? Nashr. Okay, so Rasha, when encryption text must use the same key with the binary character. Yes, Rasha, yes, we should use the same character, same key. And it's not important how long is the key, okay? It's not important whether you use a key for 8 bits, okay, or you can use the key which is, for example, 32 bits, or you use the key which is 25 bits. It's not important, okay? It's important 32 or, for example, 512 bits. Okay, it's important that any key that you use for encryption, you use the same key for decryption, and also you change the blocks in the same way. Okay. Okay. So the other method, okay, can I convert a binary number to decimal and then convert it to the letters? Yes, Haydar, you can do that. We will talk about it later, but we call it product. Okay, this is, you combine two different methods. It makes the encryption more complicated, and it's okay. It makes it more complicated, stronger. Okay, but it's possible. Yes. Okay, transposition ciphers are the other type of the cipher. If you look at the notes, you see, if you look at the notes, we talked about the substitution. So we say we had example of substitution. We say okay, and we had example of XOR one-time path. The first one was Caesar. It's okay. Now we talk about transposition. Transposition means that when for example you have ABC, you do not change the letters. You do not take the letter and put something else instead. Okay, you just change the order. For example, it can be BAC. Okay, these are the transposition methods. So one of the as an example for transposition methods, we talk about the rail fence as an example. You know what is rail, okay? Same as Farsi, I think, same as Arabic. For the trains, okay, they use rails, and the fences that they are similar to rails. In this method, okay, in this method we use a fence or a rail which is similar to fence, like this. Okay, this is similar to fences, or it's similar to the rail for the trains. Whatever you are, it's easier for you to remember. For this one, R is 2. Okay, I can draw another fence or another rail. For this one, R is 3. Sorry. And I can draw another one. 1, 2, 3, 4. For this one, R is 4. So when we have a text like hello, okay, when you have a text like hello, I will use all of these methods to encrypt the same text. You see, when R is 2, you start with H here, you put E here, you put L here and L here and then O here. Okay, you write it like this vertically, but when you want to read it, you read it horizontally, so it becomes HLOEL. Okay, this is the encrypted of hello. So with R equal to 3, it becomes H and then E and then L and then L and then O. Okay, this is with R equal to 3, so it becomes HLEOL. Okay, this is another way of encryption. Hello again with R is equal to 4, it's H and then E and then L and then L and here it's O, so it becomes HO, it becomes HOEL. You see, 3 different R, and we encrypt it into 3 different ways. Okay. Okay, so this is the reference method that we use one R or one N. Ali says, how this happen? Ali, you see, just look at the board. You see, when you want to read, when you want to write, you write this way. Okay, when you want to read, you read this way. Now you write this way, you read this way. You write this way, you read this way. Okay. Okay, inshallah. Let's go back to the slide. Here you see, now in the rail fence method, we used rail fence. For example, the example here is meet me after the toga party. Okay, this is the text. We write it like this. You can see the pointers, and then after that we read it like this. The text, or the original text, rest of the letters. What do you mean by rest of the letters? They are there. You have all the letters. We didn't remove them. Okay, you see, this is another example. Ali, just take a look. You see, the text is meet me after the toga party. Okay, so it's meet me after. Okay, here R is 2, the toga party. Okay, that's the text, and the result becomes this one. All letters are there. The original text is meet me after toga after the toga party, the toga party. Okay, this is the text. Yes, exactly, Hossein. And I appreciate if you write it in Arabic so everybody can understand. That's the meet me after the toga party, okay? And you write it vertically and you read it horizontally. So all letters should be there. Hossein, please write it in Arabic for everybody. Okay, and this is the rail fence. And then the next one. So we talked about substitution. I went to the note. We talked about transposition. It's okay. We talked about XOR, and now we talked about product. Okay, that's the last one. Yes, الترتيب عمودية والقراءة الأفقي. Thank you, Hossein. Thank you. Okay. So product, it means that you combine different methods. I think in Arabic was اختلاط, right? Combine. يجمع. Okay, يجمع, yes, or اختلاط, okay, everything, مخلوط, okay. So if you use two substitutions, something that I don't remember, one of the students mentioned earlier, when you combine two substitutions, you make it more complex, okay. When you combine two transposition, again more complex. When you combine substitution and transpositions, it's again more complex, and that's the way that we use in current methods. In today's methods, we use this concepts, okay. For example, if you have Ali, okay, and you change it with scissor n equal to 1, Ali becomes BMJ, okay. Ali becomes BMJ. Then you use, for example, I don't know, a modulation of, for example, 26. Okay, you use modulation of 26. So it becomes, for example, and you use random. It's just example, okay? The numbers I put, they are just example. It can be, for example, 002, and then 105, and then 231, okay, something like that. And then again you can use for example invert also, yeah, and you can use invert, so it becomes 231, 101, and then 002. It's very complicated to get Ali from this one because you combine, for example, substitution and the transposition methods. And this is the, we say, bridge from the old methods to the new methods. Okay, we discussed block and stream cipher, so I can skip this one. And then in block ciphers we use Fistel cipher. I will now discuss Fistel cipher. We use Fistel cipher as a method for combining all of the other methods. So again, for combining all these four, or all these three, actually, not the fourth one is product, okay. We combine, or tajmi, okay, all these three: substitution, transposition, and XOR. We combine them to make the cipher method, okay. And the method's name is Fistel cipher. It's like a large substitution combining with other methods that you already learned. So the Fistel is like this. You see, we go step by step, slowly, for you to understand. The first is that you get one big word. It can be 32 bits, or it can be 64 bits, or it can be 1 to 8. It's not important. It's just one word, because the method is important for us. You get one word and you divide it in two parts, left and right. Okay, yamin and yasar. Okay, in Arabic, yamin and yasar. Okay, left and right. Okay, so for the left word, you just use XOR to combine it with something, a function. Later I will discuss the function that it includes the right word and the key. Okay, for the left, you XOR the left one with the function that includes right and key. Okay, this is the first key for the first one, and you combine it with the right part, and then you get one result, and then you XOR it with left, and then you put the result in right part of the next level. Okay, you put in right part of the next level. Okay, but for the right part itself, you put it in the left part of the next level. Okay, so for the next level, for example, for level 2, again you do the same thing. You see, for level 2, you get the right part and put it in the left. You get the left part, XOR it and put it in the right. For the third round, again you put the right part in the left. You get the left part, XOR it with the function combining with right part and left part, and put it on the right. So in this way we make the combination very big, and computationally the number of keys that, or number of possible solutions, that's very big. Yes, we use different keys for each level. Okay, but later we will discuss it, that we generate these different keys from one unique key. Okay, we have a function that we give it one key, and then, or one main key or mother key, and then from that one we create all the keys for all the levels. Okay, so it's something like this. It's something like this. So for encryption, you get a plain text, you have n number of keys. Okay, yes Ali, still we use XOR. These are XORs, and also in F we use XOR. In F and also here we use XOR. Okay, it has all of the methods that we already taught. It has XOR, it has substitution, and it has transposition. Inside the, we call it tower. Okay, what is tower in Arabic? Inside the board. Okay, we call this one board. Okay, and usually we use it for 16 steps, or 16 times. Okay, mara, if I'm not mistaken, we use it 16 mara. Okay, and then we get the encrypted text. So for each level, function is something that does with the key and the XOR. It's not important. Inside the function you can find it on the internet. Okay, but it's not important. Something which is important, something exactly, thank you Saleh. Something which is important is that the function depends on the left side and also the key. Okay, that this is the important. Or function is a function for when you want to create a right side. Dependency of the function is very important. Okay, so for encryption you get the plain text. You have, for example, 16 keys. Okay, you have 16 keys, and 16 times you do like this. The left you XOR with the function of the key and right, put right, and the right you put it on the left 16 times. For decryption, if you use the same tower, you use the same board, okay, you give the ciphertext, just instead of starting with the first key, you start with the last key. You start with the last key and you follow the tower, and then you reach the plain text. It's same, okay? Yeah, it's cycle of XOR. Thank you. So it's same. And what this Fistel method used for, and why we taught all of them? Because they are the basis of DES. What is DES? Data encryption standard. Okay, and then after DES we have DES3, and after the DES3 we have AES, that the basic is same. Okay, and AES, A stands for Advanced Encryption Standard. What are they used for? You know, hash functions. Hash functions are based on DES. You know HTTPS? HTTPS is based on AES. You know SSL? SSL is based on AES. And Wi-Fi password is based on AES. Master and Visa card transactions all are based on AES. They all use the same thing. In all of these applications, they use the Fistel cipher or Fistel board for encryption and decryption. This is the method. This is the same method. It's a standard, okay? A standard encryption method. But how it works, it's like this. You divide all of the bits to 64 bits, blocks of 64 bits. You use 56 bits of key. You apply it on this one. How you apply it, it's the same as Fistel. You will see it later, and then you get the 64-bit of encrypted text. So inside the DES or similar AES or HTTPS or hash functions, or even in the hash function is used in, today we used it in blockchain, okay? All of them, they use the same algorithm, same standard algorithm, and also private and public keys. Okay, they also work private and public keys. They are also based on the advanced encryption standard. Okay, we have 64 bits input, and then we have permutation. It means that we change the bits. We have 16 rounds, which are all of these 60 rounds Fistel. We already discussed it. Then we have swap, and we have permutation again, and then we have 64 bits of encrypted data. Okay, and also we have one box, that in that box we from one original bit, something that Marve asked for. One original key, we create all of the 48 bits of keys. So what is inside this box? The first box is bit permutation. You see this one, permutation, one here and one here. We have two permutations, okay, and it's here. Permutation, that is that we change the place of the bits. For example, we take the bit with the number 3 and we put it in 32, for example, okay, which we change the order of the bits. We call it permutation, but it should be reversible, that we can get them back, get the text back. Okay, this is the permutation. Key generation is this one. Key generation, it's like this. You have the original key, you divide it to left and right. It has circular left shift for both of them. Okay, and then we use permutation with discard. We get 48 bits of the key, and also we get 56, again a new key, that we use this new key, put it here, and then we get the new key. Until you continue on using this function, you will get a new key. As far as you change the input, you will get the new key. So this is for key generation. And then we have another box. (16 round of DES box, which is similar to Fistel. You put the left on the right and you get the right, and then mix it with the function of the key and right, and then XOR it with the left, and here right directly go to the left comes to the XOR function, and you put it in the right. So this is the whole DES, that we have 64 bits input, you have key, and you have 64 bit output. Again, I will go back to the tower. You see, this is the tower of DES. One permutation, 16 rounds of Fistel tower, Borge Fistel, one swap, one permutation, and one box for key generation. This is how all of the encryption that we use today, they all work. Okay, if you have any question on this one, you can just ask me, because we finished this chapter for the encryptions. Anything about the Fistel tower, and then actually, you don't need to memorize everything regarding the DES. You should just understand how it works. For the exam, no need to memorize everything. Okay, if you say it's a bit complicated, I will explain it again. You see what happens from the beginning, and then we can have just have a what we can say, a small break. Okay. Okay, I will explain it again, and then I will talk about the exam. You see, consider that this is the text you want to send through the Wi-Fi. Okay, this is that I started from here. You divide that, you convert the text to the binary. So in binary, okay, in binary the text becomes this one. So this is the first step. Anything that you want to send, it converts to binary. Okay, this is the first step. The second step is the converting the stream of binary to blocks. It depends on the methods. For example, they use 64 bits. Okay, So if the block is 64 bits, it will divide the system will divide your text. Yes, we divide it into block. Okay, it will take one block. For example, consider that this is, assume that this is 64. You get one block, okay, and it will divide it into two parts, the left part and the right part, yamin and yasar. Okay, one block, one 64 bits block. Okay, it will divide it into left and right. Okay, so now the system starts doing the things, or doing the, for example, permutation or rounds or whatever it is. Okay, for example, for permutation, it's something that it does is that it changed the order of the bits inside. For example, if this is 1 1 1 0 0 0, no 1 1 1 1 0 0 0. Okay, a permutation can make it like this: 1 0 0 0 1 1 1. Okay, permutation or swap is like this. For example, another example, if it's like this, okay, the permutation can make it like this: 1 0 1 0 1 0 1 0. Okay, this is only the changing the order of the bits. Okay, they just change the order of the bits. We call this one permutation, and also swap is same. No, just permutation. Okay, this is permutation. Okay, after that, something that happens is that they put the right side in the left side of the next level. Okay, they put the right side in the left side of the next layer. Okay, or next step. They take the left side and they use XOR. They use XOR with something which is, for example, I say this one. Okay, what is this? Is that the right side, we take the right side and we take the key and we XOR them, and we generate this one. So the XOR of the left side with this output of the key, and XOR of key, for example, and the right side, we put that one here. How many times? How many times? $16 times. We repeat the same thing. Okay, 16 times we divide the block to left and right. We take the left, XOR with this one, and then put on the right, and we take the right, put it on left. So it means that you just go like this. Okay, right go to the left, again to the right, and again to the left, and again to the right. Okay, and each time you change the value of the bits. So that was permutation, and this is rounds. Okay, at the end we have swap. What is swap? In swap, for example, again you have two boxes. That's mathematically proved that 16 times is enough, for example, for today applications. Maybe in AES they use 32 times. Okay, it's computationally suitable for real-time applications, and also they say that it's safe. Okay, and the last one, what is swap? It's, for example, if this is your blocks, this is swap. So I will write here, this is swap. Okay, this is rounds, and this one is permutation. You see, I explained all of them. This is permutation, this is rounds, and this is swaps. Yes, exactly, Marva. On each block, that even now, when you listen to the lecture on Wi-Fi, for example, at your home, for all of the blocks that go out of your mobile phone or all of your system, this happens on all of those blocks. Okay, and why we use this permutation and why we use this type of, for example, number of rounds and number of bits, it's all riyaziyat. Okay, it should be proved by riyaziyat or mathematics. Prove in Arabic, I think a spot. Okay, it's a spotter riyaziyat. Okay, it's a spotter riyaziyat. Why, for example, this number of bits, or why, for example, you say this number of rounds. Okay, why this permutation? This is all riyaziyat. Okay, so this was the whole thing. Again, I will quickly go through it, and then we can have one break, a small break, and then continue on the lecture. You see, I will go back again. It's like this. So you see it, we say that, just go one slide. Okay, we say that we use block ciphers. They are safer. For block cipher we use Fistel. In Fistel you divide the input stream or input block to the left and right, and then you use the keys. For each level you use the keys, okay, in a function with the right one to XOR with the left one and put it in the right, and the right itself you put it in the left. This is the way. The evaluation in men's. I didn't get Saleh. What was that? I didn't get your sentence, Saleh. Okay, just write it in different ways. Maybe I can understand. Even if you write in Arabic, I put in Google Translate. I understand what you said. If it's difficult for you in English. So for the encryption, we use 16 steps for encryption. For decryption, we use the same thing. Only the difference is that between the keys, we start from key 0. Here for the decryption, we start with key n, or the last key. Here we start with the first key. Here we start with the last key. So the DAS standard or AES standard, that all of the security of today's systems are based on these methods, or hash or blockchain or SSL or HTTPS, is like that. you get the blocks, okay, and the clear text block, you get the encrypted, you get the encrypted, you get the decrypted using the 56 bits. How it happens is that you get the first 64 bits, one permutation, 16 round, one swap, one permutation, and then tamam. That's the encrypted text, okay, with using the 56 bit of keys. From this one key we generate 16 different keys for all of the layers in the tower. This is the permutation. You change the order of the bits, okay, but it should be invertible. This is the key generation. You get 56 bits and you get 148 bits key as an output, and also you get 56 new key for just give it back to the entrance, and then again you create a new key. Okay, and this is the DES, exactly same as the Fistel. You get the left and you use XOR with the function of the right and the key, and you get the right, put it exactly at the left side, and here is done. DES, you get 64 inputs and you have 64 encrypted output, which we say it's secure for today's applications. So in hardware gigabit per second and in software megabit per second, it can encrypt the text, but as I said, it's safe for today. I didn't mean DES. Okay, today we use AES, which is safe, number of the rounds, and also length of the block has changed. Okay, AES is a little bit different with DES, but it's the same. And also hash use the same algorithm. Hash also use the same algorithm. So this is it, and we are at 4:22. We can have a break, a small break to